Very good. Welcome back, everybody. So after yesterday's presentations that were tailored a little bit more towards calibration and speed of computing, today I would like to look a bit at nonlinear PDEs in computational finance, and particularly at American option pricing. And we will start basic with PDEs, and we will explain the problem setting to you. And in the second talk, maybe we will do some higher dimensional things. So let's get started. So again, as I mentioned, the first two have been done, the option basics and the European option pricing, the cost methods and neural networks. It turned out to, it was 4 hours, so that was done. And now we have American option pricing with PDEs first, and maybe a little bit with the cost method already. And the second lecture for today will be on the Bermudan options and the Monte Carlo method, which we call SGBM, Stochastic Grid Bundling Method. And then in the afternoon, I'm still shuffling around, but this one is for sure in the afternoon. And maybe this one will come in the afternoon. So the credit valuation adjustment with the neural networks. So we will have some neural networks in the afternoon again. And needless to say that this is joint work with many of the former students and many of the co-workers. So this talk, we will modeling American options, and American options have the early exercise feature, as you may know. We will talk about the problem formulation in quite some detail. So the model, the PDE model, and then a numerical technique. We will outline it. We'll outline PDE techniques. And also, if time permits, we will say something about the cost method for such options. And this is really like a research type, task, right, project, whereas this is more, say, the standard way to do it. With PDEs is more like the standard way to do it, and we show that we can also do it with the cost method. So for this talk today, the joint work is with Fang Fang, my PhD student from 10 years ago approximately, Swai-Cheng Liu, PhD student from last 4 years, Sander Bote, Anastasia Borovic, and Lech Krizelek. Okay, so this is what we had yesterday. Let's remember that we were dealing with a European put option. It can only be exercised at the final time, which is like here, right? It can be exercised at final time capital T. And it is the payoff for the put option is then the maximum of K minus S and 0, which is, and this should be a K then, of course, right? And so this is the put option. And here we have the value of the put option at initial time. We can compute that. It's nice if we are under the Black-Scholes world. We have a closed form solution, an analytic expression. And at any time for any stock value, we would know the option value. And then yesterday, we went from Black-Scholes to stochastic volatility. And then we saw that we have another PDE, right? We have a PDE 2D plus time. And then it's more difficult to compute the solution. So we need numerical techniques. And we have seen that for speed, we use the cost method, but otherwise we can also use finite differences. But anyway, also there, for any point in time and for any stock value, we would know the corresponding option value. Now let's look at the American option. So now the American option, of course, whereas the European option, we had my favorite picture, right? The timeline here with the final time here, time T0 here. S0 in the stock axis is over here. And in the European option, we are only allowed to exercise at final time. Now, in the case of an American option, we are allowed to exercise any time prior to the maturity time. So any time when the holder feels like it, he or she can exercise. Maybe here they need some cash, and then they can exercise. And what you get is, of course, at exercise for some value t, it is, of course, the maximum of k minus STM and 0. Right? So then you get the payoff, but the payoff which is connected to that stock value at that time. That is what you get. And in fact, most traded stock options are American style, right? The European options, they are mainly the index options, options on the whole index. But if you look at individual companies, then the listed stocks, the options on the listed stocks, they are typically American style. So they can be exercised early before the final time. And of course, the right to exercise is valuable because a holder has extra features, extra facilities, right? The holder has more rights. The right to exercise is valuable. Therefore, the value of an American option cannot be less than the value of the equivalent European option. It need not be more, but it cannot be less. Because one exercise opportunity is part of the American option, but you have many more rights, so therefore it cannot be less. And then the important question arises that when should this option be exercised? Yeah, so this is what makes the American option interesting. When should it be exercised? And also because of this, we will not have a closed form solution, not even in the Black-Scholes case. And because of this, we need to resort to numerical techniques. Okay, now, if we look back in this picture and we look at this time, for example, and we look at this solution here at t0, we have a specific feature. This picture here is a projection of that picture, this picture here. So here you have the payoff, right? Here is the payoff. And this is a picture in SV diagram, and V is the put, right? VP. So this is the payoff, and we see that, say the payoff here is for t is equal to 2. And then we look at projections of the solution for earlier time points, t1 half, t1, t a half, and t0. And we see that they are here. Yeah, they are here. And that makes sense because at S0, we have typically as a boundary condition, and we have, of course, the payoff. The payoff is the maximum of k minus S and 0. And that is, of course, when S is 0, that's k. So at S0, for any time t, for t less or equal to t, we typically say the value is k times a discount term. K times e to the power minus rt minus t. That is the value at S0 at an earlier time, so that at final time, little t is capital T, that we reach k, the value k, because this is the value k. And this value here, k times e to the power minus rt minus t, that is indeed less than k. So it makes sense that t0, t half, t1, and t1.5, they are below the payoff in this range. In this range, they are not below the payoff. You see they are above the payoff, but in this range, say from here to here, the option value is below the payoff. Now, what does that mean? It means the following. So it is for, again, it's for the European put, right? The European put in a certain S range, in this S range, is less than the payoff value. The European put at S and T is less than the payoff, the maximum of K minus ST. Now, in the case of an American option, you can exercise any time. Yeah? And in this range, should this happen in this range, then if we buy the put and we buy the stock and we exercise the put immediately, that means, say, if you exercise it immediately, because we can exercise any time, right? We can exercise the put immediately, which means we sell the stock for K. Then what we have in our wallet, we buy the option that costs us VP. We buy the stock that costs us S, and we sell the stock and we get K because we are in a put. Now, in our wallet, we would have K minus VP minus S in this specific region. Now, in this region, if this were the case, then K minus S minus VP would put this to the right-hand side. That would be greater than 0, right? So in this specific region, if we would buy an option for this value, we would exercise it immediately. When we exercise it immediately, basically it means we get this. Then we would have a profit without any risk. Yeah. So we would buy something for a cheaper price. We would immediately sell it for a higher price. That cannot be, right? That would be an arbitrage opportunity. So that cannot be. So therefore, in the case of an American option with early exercise, this region cannot exist. The solution cannot be below the payoff. If it were below the payoff, there's an opportunity to make a profit without any risk, a profit larger than putting money on a bank account without any risk. You buy it, you sell it, you exercise it immediately, and you make this profit. If that would occur in the market, everybody would do that. So that cannot be. Therefore, when early exercise is permitted, we need to prescribe a constraint to the problem. We need to say that at any time, the value of the American put option for any stock value at any time should be at least worth the payoff. It should be greater or equal to the payoff, the maximum of K minus S and 0. So here we have something which is clearly different from the European case. We impose a constraint. As otherwise, if we wouldn't impose this constraint, there would be an opportunity to make a profit without any risk, a profit larger than putting money on a bank account. All right, so that cannot be. Now let's look at a very basic free boundary example. So basically, let's look at an American option, and let's see how it works. And it's too difficult to look at the American option itself. So let's look at a contract without expiry time, without a capital T. So let's say this is a contract that can be exercised anytime. It's artificial, but for that, we can at least get to a solution, an analytic solution, or we can get to some heuristics that are important. So let's look for explanation for teaching reasons at a contract without expiry. Then the put option would only depend on S, and it's independent of T. Now, what we just mentioned, the option value cannot go below the payoff. So the value of the put should always be greater or equal to the maximum of K minus S and 0. Otherwise, we would have an arbitrage opportunity, right? Now, for the rest, the option is independent of T. And in fact, it should satisfy, at a certain range, it should satisfy the Black-Scholes equation. So we have no reason to believe that it doesn't satisfy the Black-Scholes equation in a specific region of the domain. And without time, so the dv dt term has disappeared. Without time, that is like this. 1/2 sigma square s square, the second derivative of v with respect to s, plus rs dv ds minus rv is equal to 0. Again, of course, this is under the specific assumption that the stock dynamics are geometric Brownian motion. If we do that, then the option pricing tells us we end up with a Black-Scholes type equation. And now without time, so the dvd term has disappeared. And we see here a form that is well known from calculus in the first year. In the calculus first year of studies, you have these thick books, and we typically only discuss half of the book, and in the other half, they discuss these type of problems. This is like an Eulerian differential equation, s squared second derivative, s times first derivative, and s to the 0 times the 0 derivative. And for these ordinary differential equations, and this is an ODE, it only depends on S. For these ODEs, we have an analytic solution. The solution of this ODE, VP of S, is A times S plus B times S to the power minus 2R over sigma square. And A and B are two integration constants. And the integration constants are typically defined by the boundary conditions, right? So if we substitute this solution in this equation, we see that indeed it satisfies the equation, it's equal to 0. And then A and B need to be determined with the boundary conditions. Now, what boundary conditions do we have in the case of an American option? In the case of an American put? Well, first of all, if we look back, shall I clean it a little bit? Or maybe you can see it, right? When we look back, we see that the solution typically, at least the payoff here, and also the solution you can imagine when S goes to infinity, the solution of the put would go to 0, right? That is something that is clear. Even if this is not allowed, it will look something like this. So when S goes to infinity, the put value must be equal to 0. And if we substitute that here, well, this one is S to the power minus 2R over sigma square, where R is a positive number, a non-negative number, and sigma is a positive number. So this may go to 0, all right, when S goes to infinity, but this one would go to infinity when S would go to infinity. So we need to prescribe A equals 0. So from one boundary, the boundary S, the right side boundary, S large, we would get integration constant A should be equal to 0. So this term would cancel out. Now the other side, and now we look at the other side, and basically what we look at is the following. I'll draw that picture again that we have just seen. This was S, this is the put, this is the payoff. Here is K, here is K. And we have something like this. We may have something like this, Basically, we know here, we know S large, we have already defined, and now we look here, we look at some point here. Our second boundary condition would be imposed somewhere here. We call it S star. We don't know yet where it is, right? We don't know yet where it is, but at this boundary, we would call it S star because, yeah, after that, it may be equal to the payoff. So what are the notions in the American option? When the stock is high, we don't exercise. When the stock is like here, we don't exercise. Why don't we exercise? Well, what we get is the payoff, and the payoff is equal to 0 here, right? The payoff is even equal to 0 here, because what we get is K minus S, and K minus S in this range is just 0. So we would not exercise, it would be silly, you get nothing, right? So when the stock is high, we don't exercise, yeah? Now, when it falls low here, when the stock goes down, and this is the stock direction, when the stock goes down, then one would exercise. And what you would get here is K minus S. Yeah, whenever it hits the payoff, you would get K minus S. Because then the notion is the following. Suppose that here in this range, the value of the option, VP, is more than what you get. You get K minus S, which is 0. But the value of the option is higher than that. So what you have as a holder is more than what you get. So you don't exercise. at the point where you hit the payoff, what you have in your hands, the option, is exactly what you get. You get the payoff when you exercise. So the first time it hits the payoff, you would exercise, because that is the first time that what you have is what you get. Yeah. And then it can't go lower, because that would give an arbitrage opportunity. It also cannot go higher. We know that it cannot go higher, because that would also give us an arbitrage opportunity. So if it would hit the payoff, the value may stay on the payoff. So when the stock is high, so when the stock is large, we don't exercise, because what you get is more than what you have is more than what you get. As soon as it hits this S star, yeah, let that be the value at which we exercise. So as soon as S reaches this value, as soon as S reaches this value from above, from this side, we exercise. Let's do that. Yeah. What does it mean? Well, it means that S at this S star, so let me draw it again. So we have this, something like this, right? Something like this, and this is our S star. We don't know what it is yet. Huh? We are still to determine it. But if it hits the payoff, at least what we have in our hands, the option is equal to what we get, the payoff. Option is equal to the payoff, so let's exercise. So at S is S star, the option must be equal to the payoff. So the value of the option at S is equal to S star should be equal to K minus S star. It cannot be less, otherwise it's arbitrage, and it cannot be more, because if it is more, we would not exercise. Then we have more than what we get. And so for example, here, if we would exercise here, it would be a little silly, because what we have in our hands, the VP, that's this value, it's more than what we get. We get this K minus S. All right, so let's say that at S is S star, what we have in our hands is actually what we get. That's an economic reasonable assumption. So therefore, the solution that we have reached so far was B times S to the power minus 2R over S squared. So the value of the option at S star would be B times S star to the power minus 2R over sigma squared. And that should be equal to K minus S. Yeah. So now we can eliminate at least the B. We cannot yet get a solution, because we have two unknowns and only one equation. The two unknowns are B and S star. We don't know S star yet. We don't know B. But we can eliminate B from this expression, because we can use this expression over here. We can use this relation to get only to an equation with S star. So for S larger than S star, for this range here, for S larger than S star, we know by eliminating B that the value of the put at this in this S region is K minus S star times S over S star to the power minus 2R over sigma squared. So we still have the unknown free boundary. We don't know yet where this point is. And now comes the important notion. So we choose S star in such a way that the option value at any before exercise is maximized. Yeah, we choose S star so that the DDS star of this expression is equal to 0, and we are dealing with a maximum. We want to maximize the option. Well, who wants to know what is the maximum value of the option? Of course, it is the writer wants to know that, because the writer has to make a price for the option and wants to know what is the maximum option value any time before exercise. Looking at the maximum means putting the first derivative equal to 0. Yeah, so we look at this expression, we take the derivative with respect to S star, and we put it equal to 0. Yeah, So the DDS star of this expression K minus S star times S over S star to the power minus 2R divided by sigma square. That is, in fact, even kijken, let me see. So we do product rule and we do chain rule and all these things. So we end up with 1 over S star, S over S star to the power minus 2R divided by sigma square. And what remains is minus S star plus 2R divided by sigma square times K minus S star. Yeah, so this expression here, that comes from the derivative of this term times this one in the product rule, right? Well, this term cannot be, here we cannot find a zero, here we cannot find a zero. We can only find a zero from this expression here. From this expression, we find an S star for which this is equal to 0. And then we can also verify that this is indeed a maximum for the option value. Yeah, we get an S star here. It's related to 2R sigma square and K. And with this expression for S star that we get, we can substitute it over here. And then we have the option value for a contract without time dependency. And that S star is K over 1 plus sigma square divided by 2R. This is the value that maximizes the put option value, the American put option value without time for all S larger or equal to S star. And it looks like this. If we substitute this, it looks like this. Yeah, it looks like this. The payoff is here. And then it looks like this. And in fact, it is the value for which the slope of the option value and the payoff are the same. And that slope, of course, is -1, as you can imagine, right? K minus S, the slope is -1. So it is the value. So here we have the value S star. And in this S star, the slope of the option value and the slope of the payoff, they are the same. So the American put option is maximized by an exercise strategy that makes the option value and the first derivative continuous. And then this position S star, that is called the optimal exercise point. Okay, why is this an optimal exercise point? Why would that be an optimal exercise point? Well, to look at the American option, we have to think on behalf of the writer, because the writer defines the price, right? The writer, option writer, sells the option. So the option writer defines the price. And assume that she is hedging her position by delta hedging. So she's trading in stocks and bonds in such a way that her position is delta neutral. Think of first year option pricing or introduction to financial mathematics. At delta hedging, you have the portfolio and you update it. That's delta hedging. So the position of the holder, the position of the writer in the underlying asset is delta neutral. So she is insensitive to the movement of the asset. And that is basically the basis of the Black-Scholes methodology. Yeah, dynamic hedging. So the American option writer is also hedging. So the writer doesn't care about the direction in which the stock moves. All that risk, the risk of the movement of the stock, that is eliminated by the delta hedge. However, the writer still remains exposed to the exercise strategy of the option holder. Yeah. If the writer makes an assumption about when the holder will exercise, and the assumption is incorrect, then this will have an impact on the writer's profit. So the writer is looking, when is this option maximized? When is this option worst? So the writer doesn't possibly know what the holder's exercise strategy is. It may well be that the holder at some point just needs cash in the complete portfolio. So we cannot know, as a writer, you cannot know when the holder will exercise. So how to reduce the exposure? Well, that's simple. The writer assumes that the holder will exercise at the worst possible time for the writer. Yeah, the worst possible time is the time when the option, so that the option is exercised at the time that gives the writer the least profit. So in other words, the writer looks at the option in such a way that what is the maximum value of the option? What is the worst possible time that is exercised? And that is often referred to optimal stopping time. It's not optimal for the, it may not be optimal for the holder. If the holder, if the stock goes down, when the stock goes down and we are at the payoff here, the stock goes down, then maybe the profit may increase when we move on that, when we would move on that payoff curve, right? It would always be K minus ST, and that may increase, of course, when the stock goes here. So for the holder, that may well be an interesting opportunity. But for the writer, the worst time is the time when it first hits the payoff. Out of all strategies, the writer finds the exercise strategy that gives the least value to the writer. And that is denoted by optimal stopping time. Now, again, as mentioned, the writer and the holder of the option, they may have different priorities. What is optimal for one is not at all optimal for the other. The holder may simply have a feeling about the stock or maybe speculating. The holder may not be delta hedging, right? So the holder may decide to exercise at some point. Yeah, it's highly unlikely that the exercise time of the holder will correspond to the optimal exercise time computed by the writer. Does the writer care about this? No. How does the writer feel about exercise? The writer at time zero receives a sum of money in exchange for the option. So receives the premium in exchange for the option. That premium was calculated assuming that the holder exercises at a certain optimal time, at the worst possible time for the writer. That was, the premium was based on that worst possible time. So this exercise strategy gives the option its highest theoretical value. And the writer receives this maximal amount even though the holder may exercise at any other time. Yeah. So it's clear that the writer can never lose. The worst that can happen is that the option is exercised at this theoretical optimal time, but this has already been priced into the premium that is received. All right. So that is a bit the setting of the American option. So again, the writer decides the price, and the writer decides the price based on this optimal exercise strategy, which is the worst strategy for the writer. So now what we will see when we have again my favorite picture with the put option here and the stock here, and this is the payoff. We will see that we often see, oh, this is a straight line, sorry for that. We often see things like this. Yeah, we often see option values also in time dependent setting. We often see parts. So there's some S star here. On the one hand, it's equal to the payoff. The solution of the American put is equal to the payoff. And on the other hand, here, it satisfies the Black-Scholes equation even. Yeah. So if we look at the complete setting, so remember in our artificial case, we only considered from S star to further. Now, if we consider the whole space, then we have this small piece where the option value is equal to the payoff. Let's substitute the put option value equal to the payoff. Let's substitute that in the Black-Scholes equation. Of course, dV dt is equal to 0 because there's no explicit time dependency. The second derivative is equal to 0, right? Because it's only minus S. But this one will exist, that's -1. So this is minus RS. Then minus R times V. V is K minus S. The minus RS will cancel out, and we end up with minus R times K. Well, strike price K is positive. Interest rate R is positive. So in total, with the minus sign, this is less than 0. So if we are in this region, in the region where the solution of the put is equal to the payoff, we are in fact in the range where the Black-Scholes equation is not satisfied anymore with a 0, because this is less than 0. In this part, it's equal to 0. In this part, it's less than 0. So we have an inequality. If we look at the whole range from 0 to S max, some very large number, we need to deal with the following equation. dv dt plus 1/2 sigma square S square, the second derivative of V with respect to S, plus R times S dv ds minus RV is less or equal to 0. Yeah, it's less or equal to 0 here, because in this range, it's less than 0, and in this range, it's equal to 0. So our complete problem for the American put in PDE formulation is the following. It is this inequality that we have just explained, yeah, the Black-Scholes operator less or equal to 0. Then we had this constraint that needs to be satisfied. The value of the option at any time for any stock value should be at least the payoff, cannot be less than the payoff. At final time, it should be equal to the payoff. And we also clarified that dv ds should be continuous. Again, we have seen some of these only in the time-independent case, but I can tell you that it also holds true for the time-dependent case. And so this is for the true American option. The time-dependent value, it runs until capital T. There's early exercise possible. This is the problem that needs to be solved. So it's much more involved than the problem that we are used to, right? This is not a simple equation. It has inequalities, it has constraints. How to deal with that? Well, in classical engineering, we also know these type of problems. An important notion here is that when this is satisfied with equality, the range, the S range from S star to S infinity, if you wish, this holds with equality. So we call that A, and we call this B. This holds with A holds with equality, and B holds with a strict inequality. Yeah, in that range, S star to infinity, the value is strictly larger than the payoff, and the Black-Scholes equation holds. In the range from from 0 to S star, then A, this one holds with A holds with a strict inequality, and B holds with a strict equality, right? This one, we are at the payoff in this, so that's equality, and we have just seen that this is strictly less. So there's some complementarity here. When this is equal, this is greater, this is not equal. When this is not equal, this is equal. And we will benefit from that. And that is known in classical engineering. Suppose in classical engineering, we have an obstacle. H is our obstacle. And H is positive between A and B. So here's A, here is B, and it's an obstacle, H. H is in C2. The second derivative of H is less than 0. The second derivative is always decreasing. And well, when this continues a little bit like this and like this, you see that H at -1 is less than 0, and H at 1 is also less than 0. Now, on that obstacle, we span a string, U, and the string has minimal length. And it lies on the obstacle between A and B. We don't know A and B. They are free boundaries, boundary points. We don't know A and B, but of course we can get to a problem formulation. And the problem formulation is as follows. Between -1 and A, this range, we see that the second derivative of u is equal to 0. This is just a straight line. And we see that u is larger than h. U is on top of h. It's higher than h. The same from b to 1. We see that the second derivative of u is again 0. It's a straight line, and u is larger than h. And on this part between a and b, we know that u is equal to h, and we know that the second derivative of u, the second derivative of h, is less than 0. Yeah. So in fact, we have a very similar problem from classical engineering as our American option problem. Here we have an equality, a PDE, and this is an ODE, but you understand the differential operator is equal to 0 with equality, and the constraint is strict inequality. Here we have the constraint with equality and the differential operator with strict inequality. And here also we have the equality for the PDE or for the ODE operator and the inequality here. But we don't know A and B, and that makes it difficult for numerical purposes. We don't know how to compute this. Then in classical engineering in the 70s, they came up with the following idea. Let's define the problem between -1 and 1, one problem between -1 and 1, not separate A, B, 1, -1. Let's make one problem definition from -1 to 1. We make sure that when we solve the problem, we have the whole solution. And only afterwards, a posteriori, we can determine where A and B are, because A and B will be the last points for which, for example, will be the first point for which U is equal to H and the last point for which U is equal to H. We can compute that afterwards. Let's first do a problem formulation for the whole domain. Then we get rid of A and B in the problem formulation. And that is called a linear complementarity problem. So we look at a linear complementarity problem. We see again that when U is larger than H, then the second derivative is equal to 0. And when U is H, then the second derivative is less than 0. So let's do a complementarity problem. Let's do a reformulation. And we say we look for an U in -1, 1. We look for a U in -1, 1. And we look for a U for which the second derivative times the constraint, U double prime times U minus H, is equal to 0. And with an extra constraint that minus U double prime is greater or equal to 0, and U minus H is greater or equal to 0. But let's consider this problem where at U at -1 is equal to 0, U at 1 is equal to 0. You see U at -1 is equal to 0, U at 1 is equal to 0. And we look for this nonlinear problem. We solve a nonlinear problem. And when this part is equal to 0, then this need not be equal to 0. And when this part is equal to 0, this one need not be equal to 0. And we know how to solve it. Yeah, we know how to solve it. We focus on this part. And whenever this part does not satisfy the constraint, we project the solution on the constraint. And we proceed step by step by forcing this to hold with equality. So when this one is not satisfying the constraint, we impose the constraint. We project it on the constraint. And there have been proofs in the 70s. For example, Professor Kreyer in Germany worked on this, free boundary problems. There have been proof that the solution to this equation is in fact the solution to the free boundary problem. So we do a reformulation and we solve this problem. And we have a similar complementarity problem for the American option, right? We have that when V is larger than the payoff, then we have the Black-Scholes equation. And when V is equal to the payoff, then we have the Black-Scholes inequality. So we can do a similar reformulation for the Black-Scholes equation as follows. Under geometric boundary motion, of course, the American option pricing problem can also be stated as a linear complementarity problem. It says LV is greater or equal to 0. V minus H, where H is the payoff, V minus H is greater or equal to 0, and LV is 0 or V minus H is 0. And we can compute this by multiplying the two. Yeah, so this notation here means that either LV is equal to 0 or V minus H is equal to 0 at each point in the solution domain. So LV is then dV d tau minus, so this is just the Black-Scholes operator, as you see. So how do we solve this? We solve this with projected Gauss-Seidel methods, for example, projected Gauss-Seidel. So we do finite differences. For the PDE, we can do finite differences. And at each point we look, do we satisfy the Black-Scholes equation? If we don't, and if we don't satisfy the constraint, then we should satisfy the if we don't satisfy this, we should satisfy the constraint. And then we move on. That is how projected Gauss-Seidel comes into play. Now, this is still a little bit difficult with this or sign, this one or this, or even this one looks a bit complicated, right? It's a nonlinear equation, V double prime times U minus H. That all looks a little bit involved. And in PDE literature, we have seen possibilities to replace the linear complementarity formulation by a so-called penalty formulation. Yeah, so instead of this multiplication, which looks a little bit difficult, let's look at this problem for the whole domain. For the whole domain from 0, S0 to S infinity, for the whole domain, dV d tau plus sigma square over 2, the second derivative of S times S square plus RS dV ds minus RV. And there comes an extra term, plus 1 over epsilon, the maximum of H minus V and 0. So what does this tell us? This tells us this is again a nonlinear problem, right? It has now an extra term, a so-called penalty term. And there is a positive parameter epsilon, which goes to 0. What does this tell us? It tells us that when H is not equal to V, so when this term will be dominating, right? This term will be dominating and it will ensure that V is always greater or equal to H. Yeah, so this will ensure that V is always greater or equal to H. Of course, it's also unpleasant. It's unpleasant because the quality of the solution depends on the size of epsilon, right? The epsilon tells us how much value we give to the constraint. And here we just impose the constraint. Yeah, we just say, okay, it needs to be the constraint. Here we give a specific value, 10 minus 3, 10 minus 4, 10 minus 8, maybe something like this. But the good news is that with such a problem, if we do a proper discretization, we can use classical iterative methods. We can find, we can do some, we can set up matrices for time steps, for example. We can set up matrices. We can solve these matrices with classical numerical solutions like GMRS or other iterative methods for numerical solutions. This one is always satisfying the constraint without any accuracy. We don't give away accuracy here. Here it is a little bit sensitive to the size of this penalty term. If you make the penalty too big, basically you don't satisfy the constraint. If you make it too small, you are very strict to satisfy the constraint, but it's very difficult to solve it iteratively. So we need to balance this constraint in order to satisfy the constraint, to satisfy the payoff, and also to satisfy the PDE as it is. Okay, that concludes this part for now. Let's have the 10 minutes break and then we resume.
If everything is ready, Case,
yes.
Whenever you please.
Okay, so up until now, this first hour was again to get into the problem, so to get into the American option pricing problem, and we did the PDE formulation, and this is basically quite classical work, right? The penalty formulation is very popular nowadays in PDE. And for example, Peter Forsyth from the University of Waterloo in Canada is one of the exponents in working in this. Well, we ourselves, we don't work so much with the PDEs anymore. We used to do that, but again, like in Feynman-Cutch, also in the case of optimal stopping problems, there is a stochastic formulation. So it is defined on this slide. So if we have a value function v, and it is like, say, the minimum of minus times this and v minus h. So here is again our constraint, and here is our operator, and this is like the PDE problem that we have just discussed. Here we call it the Hamilton-Jacobi-Bellman variational inequality, but it is essentially the same, right? So when the solution of the following PDE system should be found, then we can also find this as follows. We can look for a t in the time interval, and we can look for stopping times, so-called stopping times, calligraphed t. And we can define the finite horizon optimal stopping problem as follows. The v from this variational inequality is in fact found as the supremum over the stopping times of the expected value of the discounted payoff. So the expectation of e to the power minus r tau minus t, h at tau, that is the solution to this PDE. So again, we have a stochastic formulation for the PDE, and we can work on the stochastic formulation. And then x is governed by the following dynamics. dx is mu dt plus sigma d omega. So again, like in Feynman-Cutch, we have a stochastic formulation for the Hamilton-Jacobi-Bellman or for the optimal stopping problem. And this is known as dynamic programming. Yeah, we do this as dynamic programming. So we look for the solution V, which maximizes the following expectation. Yeah, it maximizes the following expectation. So how does that work? So we typically work in this formulation, yeah, in this optimal stopping problem. Because again, we have a cost method and we have a stochastic formulation by means of Monte Carlo. How does that work? Well, it works as follows. We have the time axis here from 0 to capital T. We have the stock axis here, and S0 is here. And this goes as follows. At final time, of course, we know our payoff. Yes. And then this solution here, so to discount, say, the payoff and to look for an optimal time, we start at final time. We start at final time and we look at earlier times, for example, like this, this time point M. We look at this time point and we see what is the value of continuation, the value of continuing the option. That is C in this case, and later we will call it Q at TMS. And that is the value of the expected value of the option at a later time, given that we are now at STM. So given that we are now at the knowledge level, the filtration of time M, TM, what is the expected value of the option value at a later time, and then discount it. So we look at a specific time and we look at the value of keeping the option. What is the value of keeping the option? And then this is one part of the problem. And then here we say the option value at the earlier time is the maximum of keeping the option and exercising the option. Yeah, so it's the maximum of keeping the option and exercising the option. So it makes sense. Eh? You look, and so in this range, in this whole time point Tm, in this point Tm, you look at a range and you look where, from where, say from this point on, from where is it optimal to keep the option? This is a S value, from which S value is it optimal to keep the option? Say it is optimal to keep the option here. Say it is optimal to keep the option here. And from where is it optimal to exercise? And that could be, for example, this range. Yeah. So that the combination of these two parts makes the new option value at an earlier time. Then we move on to the next time, Tm minus 1. And again, we have this value here, and that is then the option value, and we look at the earlier time, like we look for the continuation value. Again, we look for which values is it optimal? What are the values? So that is what are the values of the option, the expected value of the option at a later time point, and then discounted. So we get those values here, all these C values, we get them for any S value, we get it here. And then we say the new option value is the maximum of exercising and that continuation value. So we may get another exercise point. It may well be that here it's optimal to exercise. So to exercising means you receive the payoff and you stop the option. And here it may be optimal to continue with the option, right? Again, in a different formulation, you look at where is it optimal to keep the option, to keep it alive, and where is it optimal to exercise. And you do that for every time point. And by going backwards in time, you know that if you are at a specific time point, you always know that the decisions taken later have always been optimal. Yeah? By going backward in time, you know, and always taking optimal decisions, you know that when you are at a specific time point and you make a decision, you know that all the later decisions will be optimal. And of course, if you exercise, you stop with the option, right? When you exercise, the option contract is gone, right? You can exercise only once, and then the option contract has gone. Now, this is a Bermudan option. You can exercise it at specific times in the future. And the American option is, of course, that you can specify at any time in the future. So you would have a large time grid here in order to deal with an American option. And you would have maybe only 5 or 10 exercise points where you have a Bermudan option, and at these points you decide to exercise and stop with the option or to continue with the option. And you continue when the expected value of the option is larger than exercising. When you have more in your hands, then just getting rid of it. Yeah. And of course, at the earliest time, you cannot exercise. So you only have the discounted value of the expectation of the option at T1. And that is the value of the option at time 0. Yeah? And that is then, in fact, the value that is charged by the writer to the holder. So again, this is a completely different formulation. This is known as dynamic programming, or backward dynamic programming. It's a well-known technique. It's Bellman's principle of optimality, right? Bellman principle of optimality. And the secret is to go backward in time. The secret is to go backward in time and to always make optimal decisions. So when you are at a specific time point and you make a decision, you know that it will always be optimal in the future, as in the future optimal decisions will be taken. So what do we need in order to work with this? We need conditional expectations. Yeah, we need conditional expectations. We are at a specific point in time, at a specific stock price, because here is the stock price, at a specific point in time and at a specific stock price. And we need to know what is the value of the option, of the future value of the option. And this is the big problem in the computation of American options. How do we get to this conditional expectation? Moreover, when the S value, when this is a vector, when this is a high dimensional problem, really high dimensional problem, then it's very difficult to get to this option value. How do we get to this option value? Well, we have the cost method, as I mentioned. I will explain it, and we have Monte Carlo methods, and I will discuss Monte Carlo in detail, but it is SGBM that I like in this case. All right, so here we have the problem again with M exercise dates. We look for the continuation value, and then we look at the maximum of continuing and exercising. Well, the first thing we need is, of course, we need to determine that early exercise point. We need to determine for each time point, where is the point that the early exercise value is higher, the payoff is higher than continuing. So we use Newton's method to determine an early exercise point X star at m+1, like we had the S star in the previous lecture, and that is the root of this H at x tm+1 minus the continuation at x tm+1 equals 0. So we first need that Newton's method and determine the point. And on the one side of that point, we continue with the option, and on the other side of the point, we exercise the option. Now, we use y and x as the variables, as the independent variables. And again, this expectation that we have seen is nothing but an integral over r of the option value at a later time times the transitional probability density function, y given x in the case of a Markov process, and otherwise we do it with the filtration notation, right? So we look at the discounting e to the power minus r delta t. Delta t is a time step, the integral over r of the option value at a later point times the transitional probability function that we are at y given x dy. And then again, the v is the maximum of h and c. And the same, of course, for m+1, right? For m+1, it's also the maximum of this and this. So if we look at this function for c, and we substitute for v at time m+1, we substitute the maximum of h at time m+1 and c at time m+1, then we see if we do the cost method. So if we do the cost method, we have state variables for consecutive exercise dates, x and y. And in order to get the option value, we do a backward recursion procedure on the Fourier-cosine coefficients, which we call script h. So we will recover script h at t1 recursively from tm-1, etc., up to time t2. And if we substitute here this expression here, and again for f, you know what we do for f. For f, we approximate this with a Fourier-cosine expansion. And if we do that, we have to work on these script h cosine coefficients, and they are 2 over b minus a, the integral from a to b, the maximum of this continuation value and this payoff value times the cosine k pi y minus a b minus a dy. And again, like in the European case, we will work with the cosine and the coefficients for this value and the Fourier coefficients. Now these script h, they consist, we split the integral based on the Newton method, we split the integral, and the script h is in fact a function ck, which is defined on the interval from a to x star, and a function h, which is defined on the interval from x star to b. So again, if you think about it, so here is our S. So here's our S range. We look at a certain time here, and we see that in this part from A to X star, it is, in the case of a call, it's beneficial to continue with the option, and from X star to B, it is beneficial to exercise the option. And for a put, it's just the other way around. On this part, we have H, the payoff, and it's beneficial to exercise, and on this part, it is beneficial to continue. Now, these H values, H, they are relatively easy to compute because they are related to the payoff. So this is in fact the integral with the general x1 and x2 here, 2 over b minus a, the integral from x1 to x2 of h times the cosine dx. That is in fact, like we know it, this is like the payoff, right? This is like the payoff, and that is like in the case of the European option. We have the payoff times a cosine. This is again the maximum of s minus k or k minus s. And for that we can do a transformation so that we can do these h sub k coefficients analytically. Yeah, like in the European case, this is a payoff. Now and the other part is more difficult. This is the continuation value. The continuation value. So we should look for this one, we should look one time step earlier, and that's where the recursion comes in. So this one is again given by one time step earlier, the conditional expectation of one time step earlier, Tm plus 2. And that is how this comes in recursively. Then we have a theorem, and the theorem says the H, the capital H payoff coefficients are known analytically, and that we can understand from the previous lecture. And these C, the continuation coefficients in the American option pricing context, they can be computed in n log n operations with the fast Fourier transform. Well, how does that work? Well, if we look carefully at these C values and we start to substitute everything that we know from our option value, then we see that this is in fact the real part of the sum. Y runs from 0 to n minus 1, the sum with a dash, because the first term is multiplied by a half, times the characteristic function with a specific argument, times hj at tm plus 1, times a matrix m k comma j. And this matrix, that is the crux for the efficient implementation. So this means you write it out and you look carefully what we have in terms of Fourier cosine coefficients. And this m is then 2 divided by b minus a, the integral, and then e to the power ij pi x minus a b minus a. Hey, here we have the real part of this, times a cosine. And again, for this one, we can compute it very efficiently. And the reason is because this matrix here, this matrix, can be written as two matrices, a tuplet matrix, and a Henkel matrix. So we can write this complicated matrix in rewrite it as two matrices, a tuplets matrix and a Henkel matrix. And with a tuplets and a Henkel matrix, we can do very efficient matrix vector products. Yeah, so we can see that C as a discounting an imaginary part of MC plus MS. It's very technical, so I don't want to go in detail. I want to give you a flavor here. Yeah, I want to give you a flavor. The fact that it goes very efficiently, the details are in the paper. I think it is too tedious to explain the details. The details are in the paper. These two matrices have a special structure. And with that special structure, you can use the FFT to do the efficient computation. And that is where the n log n comes into play. We have full matrices with a special structure, a matrix vector, and the special structure is as follows. The Henkel matrix has constant anti-diagonals. Yeah, anti-diagonals are constant. Yeah, and then you can do a special, if you do matrix vector, you can just do one specific vector times the solution vector, and in fact you get the whole matrix vector product. And MS is a tuplets matrix. It has constants along the main diagonals, M1, M2, M0, M-1. And also there, if you do a matrix vector product, then by just doing one such product and doing a circulant a convolution, and as seeing this as a circulant matrix, we can solve, in fact, this one for the whole matrix vector product. By just one matrix vector, we can get to the solution of everything. And so what do? Basically, we look at this scheme very carefully. We substitute the maximum of H and C here. For H, everything is easy. For C, we need to look very carefully. What does F give us in the Fourier-cosine expansion? How can we get to this C again with one step back, going one step back in time? How can we get to all the C points? By doing that, we end up with we can resolve the integrals by very efficient matrix vector formulations. And we go backward in time and all the time back until we reach time 0, for which we get the option value. And again, with this scheme, we can get to a very, very efficient pricing of a Bermudan option with 10 early exercise dates. In the Black-Scholes world, for example, we can get a solution in 10 milliseconds, around 10 milliseconds, an error in order 10 to the power minus 9, for example. And also for more difficult Levy processes, we have the same. And yeah, we need specific choices in the cost method, but it goes very efficiently and we have exponential convergence. The details are in the paper. Yeah. Now, so what did we do? So far we talked about the American option, early exercise features. It is the fundamental nonlinear problem in finance. We look at it as a free boundary problem in PDE notation. It was reformulated as a linear complementarity problem, and it can be solved in the penalty formulation. But in our case, in our research case, we look at the equivalent formulation, that is the backward dynamic programming formulation. We need to approximate conditional expectations. How do we generalize this to high dimensional problems? Not by the cost method, because the cost method is, again, it is related to, well, you know, this is related still to dimensions. We will deal with dimensions if we go to multidimensional problems. If we go to higher dimensional problems, we really need to go to Monte Carlo. And that's part of the next part of the talk that I will show you now. Here's my Monte Carlo presentation. The Monte Carlo presentation, Monte Carlo based stochastic grid bundling method. The only difference here is that I use Q for the continuation. For the rest, it is the same. So we look at Bermudan option pricing. I would like to explain you the stochastic grid bundling method. I'll give some numerical experiments and some parallel computing experiments as well. And this is joint work with Shashi Jain, a former PhD student, now professor in India, Xian Feng, a former PhD student, now a quant in ING Bank, and Alvaro Leitao, well known in Barcelona because he was a postdoc, and now he is a postdoc in La Coruña. Okay, so let's go back to the problem, the early exercise option problem. So the value of the option, in this case, the value of the option is the supremum of the time, the t in 0 to t, of the discounting term dt times the conditional expectation under the measure q of a function of the stock, of the payoff function. In the Bermudan option, it's a little different. It is only a time in a specific discrete set of time points. This is at any time, the American option, and the Bermudan option, we can exercise at a specific set of time points. In PDEs, these type of problems are, well, also known under Hamilton-Jacobi-Bellman. And in simulation, in Monte Carlo, we know them by means of the least squares method, the Longstaff-Schwarz regression method, and we do the stochastic grid bundling method. And where do we see these features? Well, we see them as mentioned in American and Bermudan options. And mind you, we talk about stock here, but in the financial industry, it's all about interest rates and swaptions and swaps. So we have all sorts of interest rates, stochastic models, whole-wide models, and others. And also there we have Bermudan options. But there's also this, this notion that the counterparty can go in default of a contract. The counterparty of a contract can go in default. And we always want to know how much money is at stake in the future. How much is our exposure to the counterparty? And how much should we charge for the possibility that the counterparty can go in default? This is like an option pricing problem, but it is it's not pricing an option, it's looking at exposure. But later we will see that this is very similar to an option pricing problem, and that also there we need the early exercise features. In the insurance and in the pension industry, there are products like variable annuities. And these variable annuities gives you the right to a pension, basically. They preserve your pension money. And also there you look at dynamic programming, high dimensional problems, and Monte Carlo valuation with regression. And the same for dynamic portfolio management. So they are also related. Like in your pension, you'd like to invest optimally in stocks and bonds. A part of your money should go in stocks, a part should go in bonds. And that should be invested optimally. That should change over time, the composition of your portfolio. And how to do that, again, you look at conditional expectations. And with these conditional expectations, we end up with Monte Carlo valuation and regression. So how is that then doing? Well, this is basically a repetition of before. To compute the option value, it's necessary to compute the early exercise policy. At final time, the option value is the maximum of the payoff and the payoff. This is just the payoff, the maximum of H and 0. Then the Bermudan option at some time is the maximum of exercising and continuing. And continuing is here with a capital Q. And the continuation value is again the discounted value of the expected value under the risk neutral measure of the option value at the new time. Let's see how I can get this. So now, how do we do that with Monte Carlo? So we do the dynamic programming approach. We have a simulation and regression-based methods. And first we go forward in time, we generate the Monte Carlo paths. Yeah, so we generate stochastic grid points S, a vector, because we are multi-dimensions, a vector. We have S at time 0, and then we do an SDE simulation. Say we do Euler-Maruyama, or we do the Milstein, Euler-Maruyama scheme. So we make our grid points in time by going forward in time and generating these stock prices. And we do a capital N of them. Yeah, so we have m time points and we have n paths. So we have a whole forest of option of stock values. Then we reach final time. At final time, Tm equals capital T, and we can easily determine the payoff, right? We have all sort n, capital N, stock values at final time. So at final time, we can easily find the simulated payoff. And then we go backward in time. Yes. Let me see, where am I? Let me see. Yes, the next one. Okay, and how do we do that? What do? We do the following. When we are at a certain time point, we start to bundle our stock prices in different bundles. So we are at some intermediate time. We have this whole forest of of stock prices. We have this whole forest of stock prices, possibly multidimensional, and we start to bundle these stock prices into small entities. And we will approximate the option value in these bundles, in these small non-overlapping sets of partitions. The first thing we do is we try to parameterize the option values at the new time point. Because remember, we need to take the expectation of these option values at the new time point. So we try to make a functional form, and we call it Z, and it is based on parameters, coefficients alpha. So we try to represent the option value at the new time point by means of a parameterized function. Yeah, a sum of basis functions, right? Then, in order to get the continuation value at time Tm, we need to take the expectation of the option value at the new time point. But this is a parameterized function, so maybe it's easy to take the expectation, given that we are now at time Tm. And then the option value is given by the maximum of exercising and not exercising. So we have a function Z that determines inside each bundle, we have a specific function. Z, an approximation of the option value at the new time point. And the aim is to have such an approximation of the option value by which we can more easily take the conditional expectation. So we sample the distribution of S at time point Tm plus 1, conditional on the state STM, because we need a conditional expectation. And the approach is we would like to generate paths from state Tm to time step Tm plus 1. And in principle, the optimal way to do it mathematically is to do subsimulation. So from each single state point, we would need to generate a lot of paths in order to approximate that conditional expectation. But if we want to do that for each point in space, then the number of paths would grow exponentially. So that cannot be. We cannot do it for each individual point in space. We cannot release a fresh number of paths. So the alternative that we do here is we bundle the grid points at Tm. We bundle them into new non-overlapping bundles. And the paths originating from the bundle that contain x, Tm is x, they are used to sample S at the new time point. I need to do this. Let me see. So the intuition is like this. We reach a certain time point, then we have a bundle, and everything that is released from the bundle, that is considered for the conditional expectation of the new option value from the bundle, the new option value that originates from the bundle, given that we are in the bundle. Yeah, so in the limiting case, when the number of bundles and the number of paths would grow to infinity, that bundle would be equal to the point source, and that would then be equal to that subsimulation, which is too expensive. And then we do a regression, as I mentioned. This option value at the new time point, we approximate it as a regression. So again, when the bundle gets smaller and smaller, we would get a better approximation for that conditional expectation that we are here, and we want to know where are we in the next time point. So we have simulated the paths. We have S at Tm. We have S at Tm plus 1, n paths here, n paths here. And we have, essentially, we have n option values at the new time. And we want to compute this conditional expectation. The expected value of V at the new time point, given that we are at the old time point. And what we do is we regress. We use regression. So we say we can do it in two ways. Essentially, this is the classical way. We say V at the new time point is composed of a sum, K runs from 1 to capital K, of basis functions, phi K, not to be confused with the characteristic function from before. These are just basis functions. Yeah. Monomials, for example, basis functions, times a coefficient beta. Yeah, the beta comes from regression. And if we do that, then we say the polynomial is based on STM. Yeah, here, in the classical case, the polynomial is based on the earlier time step. And that means that the expected value, the conditional expectation of V at the new time point, given that we are now at the old time point, that is the expected value of the sum K runs from 1 to K, beta K, phi K as at time M. Well, because we have a filtration up to time M, we can take out what we know. So we can we can do without the expectation operator. And this expectation is then just a sum K runs from 1 to capital K of beta K times phi K. That is one way to do it. It is the basis for Longstaff-Schwarz, or for regress now Monte Carlo methods. We do it a little differently. We say we regress the option value at a later time on the basis of polynomials that are based on the stock value at a later time. So we say the value of the option at a later time point is the sum K runs from 1 to K of the regression coefficients alpha times phi K, and phi K is identified with S at the new time point. Now, if we look for the conditional expectation, in this case, the conditional expectation of V at the new time point, given that we are at the old time point, that is then, in fact, we substitute this here. That's the expected conditional expectation of the sum alpha K, phi K at S at the new time point, given that we are at the old time point. So we cannot take out what we know. This is still in the future. So this is, in fact, the sum K runs from 1 to capital K, alpha K, which we can take out of the expectation operator, times the expected value of the basis function, which depends on STM plus 1, given that we are at STM. So we need to approximate expectations of monomials. But typically that's not a big problem. If we know our monomials, we can do that. This doesn't occur, this expectation does not occur in the classical method, right? And that also has advantages. I can tell you it has advantages. But this one is just a little bit more accurate. So it basically means that our variance is smaller in this. And then we use bundling. We do this over a bundle in order to reduce this global regression, right? This is a regression, and we reduce the global regression into a local regression. And local regression is, of course, always easier. If we have a wildly varying function on the whole domain, it may be in bundles, it may still be locally with less variation, So it's better to approximate it with polynomials of a lower order in a local regression. Okay. So how do we bundle? Well, we have the recursive bifurcation technique. So this is at some time point Tm, and this is a two-dimensional cloud. And in the two-dimensional cloud, we look at the mean, and we would subdivide this into two parts, for example, in both directions. So this would be 4 bundles at this time point, based on the mean. And so the recursive bifurcation would give us 4 times 4 is 16 bundles if we choose for 16 bundles. And then we would do our local regression in each of these bundles. And even on in more points, we have these artworks. But the smaller we have our bundles, the better we can have our approximation with regression with a low order polynomial. Because you can imagine maybe they're close to linear functions in these very small size domains. Well, another clustering possibility is k-means clustering. Yeah, then we partition into bundles, and each grid point belongs to the cluster with the nearest mean. And that would look like this, another artwork. And here in both these cases, you see the dimensionality kicking in. And here you see, typically we have a two-dimensional space, and you really see the two-dimensional aspect in the bundling. And the same here. And that's unpleasant. If we go to 50 dimensions or 25 dimensions, this is really very difficult. And a way around it is to look at the reduced state space and to map the high dimensional space with the payoff as a mapping function. And then we would have a space like this, and this could be the payoff. And we would perform a so-called recursive bifurcation of grid points, and we map them to this reduced space. And then our solution would be like this, and that would be less dependent on the dimensionality. Now, how about that parametrization? We have these basis functions, phi1, phi2, phi k. We are at the new time point, and that z function that should, that is written as follows. That is what I just mentioned. It is a sum of regression coefficients in bundle beta, local regression coefficients, times these regression functions, these polynomials, and we compute alpha inside the bundle at a specific time point by the least squares regression. So we look for the alphas, and with these alphas, we determine the early exercise policy. So we look at the continuation value. It's the discounting of the expected value of this function here, of this function within a bundle. And that is then, that would then be the discounting of the sum of the k basis functions within a bundle times the regression coefficient times the expectation of the polynomial. So it basically means we need to choose our basis functions such that we can compute this expectation easily. Okay. Now SGBM, this is SGBM, regress later we called it. It's a regression based on later. It's a duality based method. We get 2 estimators, a direct estimator, that is exactly as I explained it to you. We get an option value based on the maximum of exercising and continuing. And we look at the value of the option at time 0 as the mean, as the average of the option values over the n paths. But also we have a path estimator, a so-called low biased estimation, which means that we have, based on our set of paths, we have determined the early exercise policy. We have determined which is the minimum time point at which the payoff is larger than the continuation. We only determined the early exercise policy with these points. And then we release a fresh set of paths, a fresh set of S paths. And with them, we compute the option value itself. So we use one set of paths to determine the early exercise points, and then another set of fresh paths to determine the option value. And that's a low biased estimation. So we have a high biased and a low biased estimation in our high dimensional option pricing. And these two will give us a confidence interval. Now some results. Let's look at the geometric average put option on D assets, and it has intrinsic value K minus the product of S, K minus the product of S, and we have D stocks, so S1, S2, S3, S4, etc. D stocks. The early exercise value is K minus the product to the power 1 over D. And the asset prices are assumed to follow correlated geometric Brownian motion in this case. And that means that ds over S is R minus Q dt plus sigma dw, and it's vector valued. Yeah. And the nice thing about this one is we have a reference price, because we can reduce this problem into a one-dimensional problem, essentially. So we can compute a multi-dimensional solution, and we can compare it just for academic purposes to the one-dimensional reference solution. The basis functions that we then use, the basis functions are the product of these stocks to the power 1 over D, and then to the power K. So we have the constant when K is 1. We have the function itself, the product itself, as the second basis function. The third basis function is the product to the power 2, and the third to the power 3 to the power 4. So we have these 4 basis functions. Then we need to compute these expectations of the basis functions, and we know how to do that, essentially. And the details are in the paper of the SGBM, but we know how to compute the product of such basis functions. The product of S to the power K minus 1 over D, we know how to do that. In fact, this is the closed form expression for these moments. If we look at when these basis functions are powers of the payoff, essentially powers of the payoff, then we look at the moments of these powers, the power 0, the power 1, the power 2, the power 3, the power 4. And then this is the expression for this expectation that we encounter. Well, the convergence, so here we look at two parts, and we see the convergence in the number of bundles. Yeah, it is a basket option based on 15 assets. So a 15-dimensional product, right? A 15-dimensional problem. And we have the k-means clustering, that is with the triangles. And you see this is the direct estimator, which is biased high. And this is here the path estimator with the fresh paths, which is biased low. And we see they don't really converge. But if we take this recursive bisection method, and we see that the direct estimator and the path estimator really converge to the true price. And we know the true price for this 15-dimensional case because we can reduce it to a one-dimensional case. The arithmetic average, so then the intrinsic value is K minus 1 over D times the sum of the stocks, of the deltas of the D stocks, the sum of the D stocks. Then as basis functions, we can just take, again, this part of the payoff, 1 over D times the sum, delta runs from 1 to D, as the Dth asset to the power K minus 1. So again, we have the constant. We have this part of the payoff to the power 1, to the power 2, to the power 3, and to the power 4. And also for this, we know the expectation that we need to compute. The expectation of these basis functions are given as this expression here with the factorial notation. this is, and this one we have done before. So also here we would know this, this conditional expectation of these polynomials. We know the conditional expectation, we can make use of it. Again, in the case of 15 assets, we have the k-means, which doesn't really converge, although there's only a small difference. Look at it. The option value is 1.004 versus 1.0 more or less. So there's 4 over 1,000 in between. But with the RB2 bundling, the different bundling, we have a perfect convergence. The lower and the upper bound, they converge. Okay, maybe I stop here. The time in the terms of the number of bundles, it's not so expensive for a 15-dimensional case. If we put all this knowledge in our polynomials, it converges with the RB clustering, it converges in like 15 seconds. Yeah, it converges in like 15 seconds with 15 bundles. Yeah, it's not so expensive. So let me stop here. What did I tell you for this hour? I told you we go to high dimensions. We go to the dynamic programming formulation. We work backward in time, backward dynamic programming. We always need to compute conditional expectations. We can do that with the cost method. It works, it's highly efficient when it works. However, it doesn't work in really high dimensions because there's a dimensionality issue in the cost method. But I've shown you that we can get exponential convergence, and maybe the cost method for early exercise options is even more special than the cost method for European options, because that is pretty direct. And for early exercise options, it's maybe in terms of research a bit more special. However, in order to have banking practice, we need to resort to Monte Carlo simulation. Then we can go to high dimensions. We again need to approximate these conditional expectations. And people do that typically with regression. There are two ways. One is regress now. Then the polynomials are based on S at Tm. And that is like the standard regression method. And the other one is regress later, and that is the basis for SGBM. But if we do regress later, we need to compute an expectation of the basis functions. Yeah, so we need to compute the moments, if you wish, and we prefer to do that analytically. So we prefer to choose our basis functions in such a way that we can do that analytically. By doing that, we drastically reduce the variance. So the variance is drastically reduced, which means that we can do with far fewer paths. Another nice feature is this bundling. Instead of the global regression, we use a local regression. And if we have a wildly varying function, a global regression may take a lot of polynomial terms, a high power of polynomials, cross derivatives. And if we do a local regression, we approximate such a wildly varying function locally, and locally it still looks pretty smoothly. And we can do with lower order basis functions. The details are tedious, of course, right? You need to look at these functions and what are these expectations. The details are in the slides and in the papers, but I'd like to convey this global message. The global message that conditional expectations can be done, regression forms the basis, and this is a way to do it. So let me conclude here the second lecture for today, Luis. Thank you for your attention.
Thank you very much, Kees, for the lecture.